Okay, guys, we're starting a new unit here on thermochemistry. So this unit deals with enthalpy and entropy, heats of reaction, basically. So if you'll notice, if you look at this unit outline here, it's actually pretty extensive. There's a lot of stuff that we got to cover in this unit. It used to be broken down into two units. That's why there's like two. It's chapter 6 and chapter 17. Um, because I used to do part of it in the beginning of the year and then part of it at the end. I just find it easier to do it all at once. I don't think this is an incredibly difficult concept or unit to do, so I try to do it quickly but thoroughly as well. Uh, so last year in chemistry, or the 2 years ago in chemistry, depending on when you took it, we talked a lot about enthalpy. We did a little bit about Q equals mc delta T, so calorimetry. We also talk about changes in states of matter and how that changes the energy in the system and everything like that. We do a little bit of Hess's law, talk about enthalpy. So the new stuff we're going to be talking about is the three laws of thermodynamics. We're also going to be talking about entropy, this new term entropy. And we're not going to get to entropy today. Today is just going to really be a review of all the stuff we've done in the past. Okay. So, with that said, let's get started and talk about what we have done in the past. So, let's see here. Okay. There's a lot of slides here. I should have gotten this ready before. Oh well, no big deal. Okay, so again, this is thermochemistry. Well, really, there's two different words we can use to describe it. Thermodynamics is one of the words. It's a branch of physical science. So usually when we talk about it in chemistry, we're really talking about thermodynamics. So relationship between heat and other forms of energy, such as mechanical, electrical, and chemical. And really, we're going to be focusing on chemical energy here, right? Transfers of chemical energy. So yes, thermochemistry is what we're really mostly going to be focused on. Okay, so thermodynamics is the larger term that encompasses thermochemistry, but really we're talking about thermochemistry. And if we look at a reaction diagram here, when we're talking about thermochemistry, we're talking about this part, the reactants and the products. So from here to here, this is the realm. So everything in red is the realm of thermodynamics or thermochemistry. Okay. Everything in the middle here that deals with this transition state, that is kinetics. And we'll get to that later. So how fast a reaction occurs, basically. Is basically what they're saying when we talk about kinetics. Okay. But thermochemistry is only concerned with the beginning and the end. What happens from the beginning to the end? Okay. So a couple things. Energy, the ability to do work, produce heat. It's equal to the kinetic energy plus the potential energy and the internal energy system. Okay. Potential energy is energy by position. And usually when we're talking about potential energy in chemistry, we're talking about chemical bonds. Okay, chemical bonds. And where the energy is related to is really the Coulombic attraction. So we'll talk more about Coulombic attraction later on when we talk about bonding and stuff like that. But Coulombic attraction is really important when we're talking about the bond energy. Okay, when atoms bond, energy is released, and when bonds are separated, energy is absorbed. Usually, not always, but usually. Okay. Kinetic energy is energy of motion, 1/2 mv squared. Okay, it depends on the velocity of particles and their mass. Okay, the first law of thermodynamics. First law of thermodynamics states that the energy of the universe is constant. It's also known as the law of conservation of energy. So energy cannot be created or destroyed, Whatever you put in, got to come out. They're equal. Okay. Okay. Thermochemistry and heat. So heat we usually represent with this letter Q. Don't ask me why it's a Q. I forget. I'm sure you can look it up and find out why. But we're talking specifically about heat. We use the term Q. Okay. Heat always goes from hot to cold. Okay, remember temperature is not a measure of energy. It just reflects the motion of the particles. So the average kinetic energy of the particles. Remember, temperature is proportional to the average kinetic energy of the molecules. Often, heat them up, you speed them up. Hear that term, or hear that phrase sometimes. Energy and work. So energy is we often define energy as the ability to do work. So energy is actually the amount of heat plus the amount of work. Okay, if heat is absorbed, it's endothermic, and we call it a plus. Put a plus sign on it. If heat is released, it's exothermic. We put a negative sign on it. The sign for W is whether work has been done by or on the system, or on the gas. If work is done on the system, i.e., like we compress it, so we're compressing something, then work is positive. If work is done by the system, then it's a negative. Okay, and work equals negative P delta V. You should memorize this. Sometimes there's a question on the exam about that. So on the AP exam, so work equals negative P delta V. So do remember that. Okay, calculate delta E for an endothermic process, which 15 kilojoules of heat flows, and there's 1.4 kilojoules of work done on the system. So both of these are positive, positive, positive. So you just add them, you get 17. Okay, calculate the work associated. So this is negative P delta V. I forgot to write the delta, just wrote the V. Negative P delta V. So 15 or negative 15 ATM times change in volume, which is, this is positive, so 64 minus 46, and you get that answer there. Pretty simple stuff. Okay, and this is the answer to this one. I'm not even going to do this one. Okay, because you have to convert a bunch of things. I don't feel like converting it. Do it. Check your answer. That should be the answer right there. All right, this term enthalpy. So enthalpy is a thermodynamic quantity. It's equivalent to the total heat content of a system. It's equal to the internal energy of the system plus the product of the pressure and volume. Most of the time, we're not going to be changing the pressure and volume, so it's really just the internal energy of the system. Most of the time, we're keeping these constant. Not always, but most of the time. Okay. Now, to measure the change in enthalpy is the difference between the enthalpy of the products and the reactants. So it doesn't matter how you get there. Like, so in this, if we're looking at this reaction here, it doesn't matter that there's only one transition state here. If this were to occur and go through several different things and do whatever here, this stuff doesn't matter. The transition doesn't matter. It only matters what the beginning and the end, what happened in the beginning and the end. This realm is kinetics, okay? How it gets from point A to point B is irrelevant in thermodynamics. How it gets to point A to point B is the realm of kinetics, okay? So we're not even going to worry about kinetics right now. We're just going to worry about A to B state function. Only doesn't, the pathway doesn't matter, okay? If pressure is constant, Q equals delta H. Okay, and that's for the most of the time, this is going to be what we're dealing with. Okay, and we're going to be able to calculate enthalpy a number of different ways. Okay, stoichiometrically, using calorimetry from tables of standard values, Hess's law, and bond energies. Bunch of different ways. I'm going to show you how to do each one of those ways. Today, we're probably only going to get to really calorimetry. Okay, exo versus endothermic. So this should be a little bit of review from chemistry. Exo, heat is leaving the system. Exo, exit. Leaves. Oops. Leaves the system. So we lose energy. Reactants to products, we have less energy. Okay, energy is released. Exothermic exits. Endothermic. Endothermic enters the system. So there's going to be more heat from the beginning. Okay, so we start lower, get more. So energy is absorbed. Really simple. I hope you all are able to do that. Okay, this is one way to figure out change in enthalpy. So this is the stoichiometric way. In the stoichiometric way, usually the heat is either in the products or reactants. If it's in the products, that's exothermic. If it's in the reactants, it's endothermic. Okay, so here, upon adding solid potassium hydroxide pellets to water, the following reaction takes place. So we have KOH dissolving and giving up that much heat. So if we have 14 grams of KOH, first of all, it's releasing the energy. It's releasing it. Where is that energy going? It's going to go to the water, to the surroundings. It's going to go into the water. It's going to go into the beaker. So it should get warmer. Okay, it's exothermic. The heat is being released. Okay, if we have 14 grams of KOH, first thing we have to do is convert that to moles. So KOH is 56 grams per mole. 1 mole, 56 grams. And then we can use molar ratio. So we could say that there's 43 kilojoules released every 1 mole of reaction, or every 1 mole of KOH. Okay, and when we do that, we should get 10.7. And because it's exothermic, it's negative. So negative 10.7. Horrible handwriting there, but whatever. Okay, so that is the stoichiometric way. Pretty simple. Next, we're going to deal with calorimetry using the calorimeter method. So this is a really, really simple calorimeter. A calorimeter is something that measures calories. Okay, a calorie meter, right? Thermometer measures thermal heat energy. Calorimeter measures the amount of calories. Okay, and calories are the units for heat. Okay, so 1 calorie, we use calories and we use also joules. 1 calorie is 4.184 joules. Those are the 2 units we use. Okay, and a calorimeter measures the amount of calories that are released or absorbed in a chemical reaction. Okay, so in this coffee cup calorimetry here, we have 2 coffee cups. You actually just could have 1, but 2 is a better insulator. We want to try and minimize the amount of heat that's absorbed or released from the outside here, right? We want to insulate it from the outside. Okay, we're going to have a reaction occur in here. The reaction is either going to heat up the temperature or cool down the temperature of the water. Okay. We'll know the temperature, the change in temperature of the water. We'll also know the mass of the water because we're going to measure that before we do anything. Okay. From that information, we can find out how much heat energy is released. So let's do a problem like that. All right, I guess let's talk about what some of these other terms we need to know. Heat capacity is the energy required to raise the temperature of something, anything, by 1 degree Celsius. Mass is not important here. If you're looking at like a piece of paper, then it's how much energy is required to raise that piece of paper by 1 degree Celsius. If you're looking at a cup, how much is required for that cup, so on and so forth. Specific heat capacity, that is abbreviated with C, but it's specific to 1 gram of a substance. Okay, so how much energy does it take to heat 1 gram of this specific substance by 1 degree Celsius? Okay. Molar heat capacity, same as the specific heat capacity, but we're talking about 1 mole of a substance. Okay. One of the most important equations we're going to use, and this we're using for calorimetry too, is Q equals MCAT. Q equals MC delta T. Q is the quantity of heat released or absorbed. Again, negative it's released, positive if it's absorbed. M is the mass. M is the mass of whatever you're taking the temperature of. M is the mass of whatever you're taking the temperature of. Delta T is the change in temperature of whatever you're taking the temperature of. And it's T final minus T initial. And C is that term specific heat. Now, every substance has its own specific heat capacity. Water has a specific heat of 1 calorie per gram degree Celsius, or 4.184 joules per gram degree Celsius. You'll mostly be using the joules one. Okay, so as I said before, specific heat of water, 4.184 in its liquid state. It does change based on state of matter. So ice and steam have different specific heats. Okay. Every substance has a different specific heat. All right. So water has a very high specific heat compared to most things, and that's really what makes life on Earth possible. We can go into different surroundings, 90 degrees Celsius, there's not 90 degrees Celsius, we die, 90 degrees Fahrenheit or 10 degrees Fahrenheit, and we still survive. We don't die because most of our body is made of water, and the water can regulate our temperature pretty well. Okay. I said this already, calorie, joules. You may see kilocalories. The calories you'll see a lowercase c, and these are science calories, science ones. These are the ones that we're going to be concerned with. If you actually see calories on a food label, you'll see that it always has a capital C, and these are actually kilocalories. So it's actually 1,000 little calories. So if you look at like Japanese or European products, you'll actually see that they say kcal on them. They'll say kcal rather than just calories. Okay, because they're actually kilocalories. Okay, so there's some problems here. We can go over these in class if you like. I don't want to. I'm not going to take too much time to go over them. The answers are here and here. I guess I could show you how to set it up, maybe. In a coffee cup calorimeter, 100 milliliters of 1 milliliter NaOH and 100 milliliters of 1 molar HCl are mixed. Both solutions were originally at 24 degrees Celsius. After the reaction, the final temperature is 31 degrees Celsius. Assuming the solutions all have the same density and a specific heat capacity of 4.184, calculate the enthalpy change. So we're looking at Q here, or Q equals delta H here, because we're not changing the pressure. and it's going to be equal to mc delta T. The mass here, each milliliter is 1 gram, and there's 200 milliliters, so it's 200 grams of water. The specific heat, we're going to use the specific heat of water, so it's 4.184 joules. Be careful, this is in joules, the answer is in kilojoules, so whatever answer you get here, you have to divide by 1,000. It times the change in temperature, so it's always final minus initial, so 31.3 minus 24.6. That's how you set it up. All right, now the question is, do you need to use Kelvin or Celsius? It doesn't matter for these ones because it's the change. We're always going to be doing the change. And for Kelvin, it's just you're adding 273 to both of these, so it wouldn't change the answer at all. The answer is in Kelvin or Celsius will be the same. Okay. Next one, number 6, is just like the other one we did. This is the use stoichiometry to solve this one. Okay, I don't want to take too much time to do those. Let's see here. 1 milliliter of 1 molar BaNO3, solution 25. Mixed with another solution 25. It's the same thing you just did before. Yeah. Oh, this one they want per mole. So per mole. So you have to figure out how much energy is released, just like we did before. And then this is 1 molar in 1 liter, so 1 mole per liter. That's the molarity. Times 1 liter will give you 1 mole. So this is kind of stupid because it's whatever you get for the amount of kilojoules is just divided by 1. So same thing. Okay, I'm going to stop there for this part. I do want to go and talk really quickly about, well, actually, you know what? I'll say that for class. So, yeah, I'll save the problem for class on Monday. So we'll talk about the problems on Monday. All right. That is all.